as we continue our lecture series, it's time to welcome our next esteemed speaker of the day, Dr. Litty Allen Verghese. So, before that, let me take a moment to introduce our speaker. Dr. Litty Allen Verghese is a distinguished professor at the Department of Chemical Engineering, NIT Calicut. She obtained her BTech in Chemical Engineering from Government Engineering College, Thrissur, followed by an MTech and PhD in Polymer Technology from Cochin University of Science and Technology. With a robust academic background, she has been a part of NIT since 2008, contributing significantly to both research and teaching. Her research interests include polymer technology, adhesives and surface coatings, and nanocomposites. She has an impressive portfolio of 45 publications, including journal articles, book chapters, and reviews. Her work has garnered over 600 citations, reflecting her impact in the field. In addition to her academic pursuits, Dr. Litty Allen Verghese serves as the chairperson of the Center for Quality Assurance and Enhancement at NIT Calicut, highlighting her commitment to institutional development and excellence. Please join me in welcoming Dr. Litty Allen Verghese to our next session.
So good afternoon all, and thank you very much for the nice introduction about me. And so I am a faculty here in the Department of Chemical Engineering. I thank Professor Unnikrishnan sir and Professor Raju for inviting me for a session on adhesive properties of bio-based biocomposites. This talk will be a general one, finding the basic things about adhesives and biocomposites. Because as you know, these days, you were listening about biocomposites. So you know that any composite material, it has a matrix as well as a fiber. So we can say that a biocomposite can be a material, either it can be a biofiller and a non-biopolymer, or a biofiller and a biopolymer, or a non-biofiller or a biopolymer. So either the matrix should be a natural origin, or the fiber should be of origin. So this biocomposites, based on this general classification, it can be matrix, based on matrix, it can be classified into thermosets, thermoplastics. Like thermoset, you know, epoxy, polyester, urethane, phenolic resins, etc. While thermoplastic, polyethylene, polypropylene. And fibers can be either natural or synthetic. Natural, few examples are given. Synthetic, like nylon, polyester, etc., can also be used. So all this broadly comes under biocomposites. So depending on the type of polymer matrix employed, such as thermoplastics or thermoplastic, the characteristics of biocomposite will change. And so we have biocomposite, and so inside that filler should be there. So filler has to be adhered properly to the matrix. So what is adhesion? Adhesion is attraction process between dissimilar surface that cling one another. And so the opposite is cohesion. Cohesion is when it is between when two similar materials cling, we call it as cohesion, and adhesion means two dissimilar surfaces that when it clings together, we call it as a adhesion process. And the properties shown by the materials that show adhesion, it is known as adhesives, and adhesives are substances that facilitate the sticking, holding materials together through surface treatment. And the intermolecular forces responsible for the function of various kinds of stickers, sticky tape, all this comes under chemical adhesion, dispersive adhesion or diffusive adhesion. So we know that there are different types, there are different mechanisms by which these two materials will adhere together. So we will see what are the mechanisms of adhesion. So the important theories of adhesion, one, it is physical adsorption. Then it can be either it can be chemical bonding, or it can be diffusion theory, or even electrostatic theory, or mechanical interlocking. So we will just see each of them. So physical adsorption theory means there is contact between two materials on the surface, and there will be van der Waals forces of attraction that holds the two adherent and the adhesive together. So for these forces to develop, in order to have a good bonding between these things, they should come in contact. Intimate contact should be there, molecular between the adhesive and the adherent. So we call it as, that is, proper wetting should be there for the on the surface. So wetting can be determined by contact angle measurements. So you can see here that this adhesive chain, it is shown by the blue line, and van der Waals, this there's a physical interlocking is happening at this thing. So that is physical adsorption. So wetting should be there. So what is wetting? So a complete spontaneous wetting occurs when the contact angle you may be familiar. So that is when a drop of fluid falls on the surface, what is the angle it makes with the surface. So when the contact angle is 0 degree, or the materials, then the material will spread uniformly over the surface and form a thin sheet. So that we call it as a complete spontaneous wetting. So how is it possible? How can we have a 0 contact angle? So when the substrate energy, that is critical surface energy of the substrate, is high compared to the adhesive, that is compared to the surface tension of the wetting liquid, we call that, it favors the wetting process, that is C of substrate should be greater than the C of adhesive. So we can say that low energy polymers easily wet high energy substrates. If the substrate is having higher energy, the low energy polymers can wet it. But few substrates with high energy, low surface energy, like polyethylene or our Teflon, fluorocarbons, etc., you know that material won't stick to that, because they are having low surface energy, and it is difficult for them to higher energy thing to stick on it. So they will be primarily used for non-stick and passive surfaces. We call it as non-stick surface or passive surfaces. So in order to have a good wetting, the surface energy of the substrate should be higher. So this will give you an idea of different types of wetting process. One, it is 0 wetting, that is super wetting or super wicking, where the contact angle is 0. While it is super hydrophilic, we call it as less than 10, then hydrophilic 10 to 90 degree. And if the contact angle is between 90 to 150, hydrophobic, super hydrophobic, rose petal effect and lotus effect. So this is how it is classified different based on the contact angle, the nature of the surface. So that is a physical bonding. So physical bonding, a van der Waals force of attraction is required, and for that proper wetting of the surface is required. Second is chemical bonding theory. Chemical bonding theory states that there should be an ionic bond or a covalent bond has to be formed between the adhesive and the adherent. So we can say that we will add some silane coupling agents or adhesion promoters. We will add into the adhesive system so that it can react with the adherent and form a chemical bond between this adhesive and the adherent. Another example is some isocyanate groups can be there in the adhesive system. So that can react with the hydroxyl groups present on the adherent surface. That gives a permanent bond. Then the third one, it is diffusive adhesion. Diffusive adhesion means both the material adherent and the adhesive, they should be mobile. That is, both materials are mobile and they should be soluble in each other. So this would be particularly effective with polymer chains with one end of the molecule diffuses into the other material. That is, they should be, see, adhesive and substrate, there should be mutual interdiffusion should happen between these two. So they should be mutually compatible, and the different parameters that affect this diffusion process is that contact time, how long it is in contact, then temperature, molecular weight of the polymers, physical form, whether it is liquid and solid. And it is observed that generally polarity increases the adhesion, and the limitation of this diffusion theory is that if the molecular is highly crystalline, or it is a long chain or high molecular weight, so that it won't be soluble. So that is the diffusion theory limited application where the polymer and adherent are not soluble, or that there is no chain movement because it should be mobile, and it is constrained by its highly cross-linked crystalline structure, or when it is below its glass transition temperature. When a material polymer is below its glass transition temperature, it will be brittle or rigid. So in that case also diffusion theory of adhesion cannot be possible. So this is commonly, this diffusion theory can be seen in rubbery polymers and in the solvent welding of thermoplastics. Like an example is polystyrene. It is a polystyrene can be, two polystyrene surfaces can be swelled using a butanol solvent, and then it can be pressed together. The solvent has the lowering, effect of lowering the glass transition temperature below ambient. So while interdiffusion takes place and later it gets evaporated, so the two surfaces will get adhered together. Then the next theory is electrostatic theory of adhesion. So electrostatic theory means there will be a charge developed, like in a capacitor, there will be a plus charge and a negative charge. So at the interface between the adhesion and the adhesive, there will be a charge will be developed, positive and negative electrostatic. So an electrostatic force or a Coulombic force between the two materials will happen, and that will bond the two surfaces, that is adhesive and the adherent together. So we can say that there will be an electrical double layer between the adhesive and the adherent. So this says that adhesion occurs due to electrostatic forces between the adhesive and the adherent, potentially involving the formation of an electrical double layer. That is, you can see on the substrate negative charges and this one positive charges, slight positive charges. So that forces joins them together. But normally in polymers we know that it is insulators. So only so normal insulator type polymers we cannot, this theory is not that significant. While if some conductive things etc., this electrostatic theory can also explain the adhesive nature between a substrate and the adhesive. Then the last one is mechanical adhesion. Mechanical adhesion means, see, when you are taking any material and to join them, first we will have to do some surface treatment so that some peaks or this one, that openings, pores can be formed, and this while pasting this adhesive on the, rubbing this adhesive on the surface, these adhesives can penetrate into these holes or pores or openings, and later they will cross link and harden, and that forms a that is how the mechanical adhesion will takes place. So for mechanical adhesion to takes place, so adhesive flowing and filling micro cavities on the substrate, and the adhesive, when it hardens, the substrates are held together mechanically. So for mechanical adhesion, the surface roughness should be there. It should not be a plain surface. Surface roughness should be there. So that surface roughness, when you are doing some surface treatment, the roughening your surface, especially roughening your surface, it gives teeth to the substrate. That is, some mechanical interlocking effects will be given, and it increases the total effective area over which the forces of adhesion can develop. So we can say it is a valley and maze like thing. So roughening is, but roughening is only effective if the adhesive can wet properly the adherent. So these are the main theories of adhesion: physical, chemical, then electrostatic, diffusion, and mechanical interlocking. So then we have, whenever you are going to apply an adhesive on the system, there should be, we have to do some surface treatment to the substrate. So when it is mechanical roughening, you can use this emery paper, you will be rubbing with that, so that surface will become rough, and mechanical, that is, we are aiding in that mechanical interlocking thing. Then we can have chemical treatment. Based on whatever substrate we are using, we have to judicially select the different treatment methods, like acid etching will be there, alkaline etching will be there. So, but I think whenever you are doing a chemical treatment, immediately after that you have to clean it, solvent wiping and etc. has to be done. Then in some cases, even plasma treatment, ionic gases can be used for this surface treatment. So these are the different methods commonly practiced in industry to improve the adhesion property of the adhesives. So whatever be the treatment, pre-treatment methods always enhance adhesion, and this pre-treatment produces micro roughness on the surface, so which can improve the bond strength and durability by providing mechanical interlocking and enhancement of adhesive strength due to the roughing of the adherent surface may also result from other factors like large surface area is increasing, then kinetics of wetting is changing, and plastic deformation also is increased. So what are the normal adhesives that are used in biocomposites? We can say natural adhesives are there, lignin, soy protein, starch-based adhesives. These are few examples. And synthetic adhesives like epoxy, polyurethane, phenolic resins can be used. Then sometimes there can be a hybrid adhesive. It can be a combination of natural and synthetic. But more often we can see that it is a combination of two different chemistry, like synthetic adhesives of having two different chemistries, like epoxy and acrylates can be used together, like that. So it can be either natural adhesives, synthetic adhesives, or hybrid adhesives can be used. And what are the factors that generally affect the adhesive properties? One, it is fiber matrix interface plays a crucial role in adhesive performance. Then moisture content, like is fiber matrix interface, we'll see in the next coming slide. Moisture content, like the presence of moisture will affect, will promote degradation in adhesives. Temperature, see when it can, it should sometimes if it goes below the TG glass transition temperature, the properties expected from the system can be different. And surface energy, as we told earlier, it plays a crucial role on selecting the substrates and surface preparation. And it is reported that even that contamination, oxide layer or organic contaminants on that is present on the surface of these adherents, it will affect the property of adhesion. So simple removing, that is mechanical roughening and removing this oxide layer or organic contaminants itself is increasing the adhesive property to a higher level. So you can see an abraded surface in that second picture, that is we are abrading using some emery paper, surface energy low, high, and contamination. And how you can test these adhesives? So adhesives, common test is shear test, which is done as per ASMD 1002. So it measures the shear strength of adhesives. That is, it will be like a shearing of one will be, and it will be sheared off. ASM D1002, and peel test, either it can be 180-degree peel test or T peel test will be there. So evaluates the adhesive strength in peel mode. Generally adhesives will be less strong in peel test, while it is more it shows more values for lab shear stress. Then it is done as per ASM D903 or ASM D1876. Then pull off test is there, which assess the normal tensile strength of the adhesive. And also dynamic mechanical, as previous lecture you heard, dynamic mechanical analysis also measures the viscoelastic properties of the adhesives. And how will you classify these adhesives? We know that when it is in service, this will fail. So the failure can be of three types. First one, it is adhesive failure or interface failure. Interface failure or adhesive failure means it occurs when there is minimal adhesion on one or both sides of the bonding surface. That is, this is adhesive or interface failure. That is, there is a one from the one surface, it is separate, it is clean, it is separated. This is adhesive layer and this is a second surface. So there is clean separation between the adhesive and the adherent. And another type of thing can be cohesive failure. Cohesive failure means that is the failure is happening through the adhesive. So few part of adhesive layer you can see stick on to that, and few part it is there. And substrate or adherent failure means the substrate fails during this adhesive treatment. So adhesive or interface failure occurs when there is minimal adhesion on one side or both sides of the bonding surface. So it occurs generally observed in low energy level surfaces, because proper bonding is not happening with the of the adhesive with the surface. So it is easily separated from that surface, and it occurs due to inability to develop a chemical bond between this adhesive and the substrate. And also it can happen when the adhesive cures before a bond is established. Adhesive itself can cure. So when an adhesive, if it cures before establishing a bond between the adhesive and the adherent also, this adhesion failure can occur because adhesive itself is cured, so it does not have any contact with the or a bond formation between the adhesive and the adherent. So in that case also that adhesive failure can occur, and operational and environmental factors can also contribute to the adhesive failure propagation. And next is cohesive failure. Cohesive failure, this failure modes that is through the adhesive. So it can occur due to shear stress, peel stress, or a combination of both stresses. And also it can happen, that is when there is no stress distribution happening in the joint, we can say that a cohesive failure is happening. So bond line can be too thick. Actually, studies are conducted to see what is the thickness of the bond line in order to have better adhesion. So it is found that generally 2 to 4 mm thickness is good. So if it is more or less, it is that failure is higher. So bond line thickness and uniformity in bonding that layering also. Sometimes it is done using brushing or something. So that how uniformly you can coat the adhesive on the surface of the substrate also plays a crucial role. And another thing of cohesive failure is that adhesive does not have enough strength and it is too soft. And also if it is there some pores or something etc., that also can lead to cohesive failure. This substrate failure or adherent failure occurs when the mechanical strength of the substrate is lower than the adhesive bond strength. So that will clearly tell you that this particular system of adhesive is not suitable for that particular substrates. So that you have to change the adhesive system, or you have to change the adhesive, or you have to change the substrate because it cannot withstand the substrate or adherent failure. And this will give you a typical picture of different combined picture. All these things will not happen together in an adhesive joint. Just a typical figure shows that typical defects that can happen in an adhesive joints. So this adhesive joint defects can be either it can happen in the adherent, or it can happen in the interface, or it can be due to the adhesive itself. So these are the defects that can happen in the interface. One, it is called a kissing bond defect. Kissing bond defects means we will see that it is bonding very closely or in that joint perfectly well, but actually there is no bond formation is happening between the adhesive and the adherent. So that type of thing, it is not that type of defect, we call it as a kissing bond effect. Or we can have debond or delamination. After peeling off, you can see that some part of the adhesive is coming out, or the debonding or delamination is happening. So otherwise, then we have either it can happen with the poor curing. That is, as we mentioned earlier, the adhesive is not cured properly, so it is soft and it has not attained the proper strength. So poor curing is another thing. Then this is pure fillet and geometry. That is how this adhesive behaves. Adhesive behaves means when you are pasting this, if there is a geometrical change or a spew fillet, like there is a angle or it is not uniformly filled, there will be stress concentration, and that can act as a defect. Then if some cracks are there in the adhesive, that can act as a defect in the adhesives. And another thing is that, see, some chemical reactions are happening. So if some molecules like water molecules, etc., or small molecules are evolving, so if you are not giving enough time to that is remove that from the system, that will cause small voids or pores inside this adhesive layer. And also this porosity of the adhesives also can be there, like solvent is not escaped properly. Then also when during the curing, the solvent will escape, and that region there can happen porosity. And surface corrosion, that is That is based on the adherent performance. That is, if the surface is corroded, after some time if the surface is corroding, that can also act as a weak point where the adhesive will fail. And poor adhesive filling, that is distribution of the adhesive on the surface of this substrate, that can also act as. So altogether these are showing few mechanisms by which the adhesives joints fails under service or during testing. These are the reasons. And coming to the application of biocomposites, you may be hearing for this past 1 week. So it is used in automotive industry. So lightweight panels, bonding of car bodies, many things it is happening now. And even my research group, Dr. Habib is here. They are developing some undercoat applications based on polyester resin and all. So then construction in sustainable building materials can be prepared using the biocomposites. Then aerospace eco-friendly structural components are there. Then the most familiar thing is biomedical application, that UV curing cements in dentistry and acrylic bond cements in orthopedic surgery, etc. So all these things find application, that is, this biocomposites find application in all these different things. And apart from this acting as an adhesive, adhesion is essential for this printing ink, our painting and other surface coating. And in rubber tire industry, there should be proper adhesion should be there between the steel and the rubber. And also in glass or carbon fiber in plastic, any composites adhesion, apart from this adhesive nature, adhesive joining two things together, they should have that property of adhesion is essential in all these applications. So what are the advantages of adhesive joints? They can join dissimilar materials, and thin sheet materials also can be joined, while mechanical fastening will be difficult in very thin sheet materials. And the spreading of load over a wide area is possible. And aesthetic and aerodynamic exterior joints, any shape or any different things you can join using adhesives. And even now machinized coating is there, application by machine or robots it is possible. But the limitation is that generally it is weakened by water and its vapor, because water because every most of the adhesives it will be exposed to environment, but water is there. So water and its vapor can degrade these adhesives. And the service temperature also, it cannot be like a mechanical fasteners, nuts and screws if you are using, it can be used for a wide range of temperature. But there is a limitation for polymeric adhesives. We have to see that operation temperature, it should be within a specific limits based on the what type of adhesives or polymers we are using and a degradation. So these are the limitations of this one. So what are the challenges and future directions for this biocomposites and the role of adhesives? So one major challenge is moisture sensitivity, because we have seen it as a limitation of the adhesives. Then this fiber, if you are using a biofiber, you can see that from the nature we are collecting, so it varies from time to time. Then the inconsistent fiber properties. And so, and another one is adhesion durability, how long it can be used and water under different service conditions. So the future research focuses on enhanced bio-based adhesives, and you can utilize nanomaterial reinforcement for improving the strength of the adhesives, and improved surface treatments can be possible. Generally now what followed is that typical processes like degreasing, solvent cleaning, etching, all these things. So other improved surface treatments also can be possible. And sustainability focus on renewable resources and recyclability, because most of it is thermosets. So once it is used, cannot be recycled. So that way also future directions work can be focused. So a true bone grows stronger with every challenge it conquers. So thank you.
Thank you, ma'am. The session is open for discussion.
So actually it is a basic theory on adhesion.
I have one not question, maybe little reinforcing what you said. The for cohesive failure of the product, mean or the even two between the two materials. So one biggest challenges what I have seen industrial point of view, of course, that moisture. Other than that, the surface preparations.
Surface preparation,
People
correct.
generally won't consider too much on the surface preparation. They just put say example adhesive is there. They just supply it on the surface, then stick together. They say better. They expect better adhesion, but that is not the case. Either like you said, emery paper, or maybe like sandblasting, where industry do this particular operations before joining any of these two materials. So my thinking would be like on bio-based adhesives, this lignin, this cardinol, or maybe this kind of adhesive system also may be a good adherent or maybe good adhesives, but I think there could be some modification to be done
Yeah, some
to meet this kind of industrial requirement point of view.
correct. Even surface treatment after that surface cleaning also is very
Yeah,
must
surface
because
cleaning.
any contaminants present it act as a weak point for that.
Correct, correct. Students.
Ma'am, is there any relationship between the thickness? Suppose you have mentioned some painting and all the
Yeah, that is
adhesives.
better. That is, it is found that the thickness should be uniform and also it should be within the range of 2 to 4 mm will be better. But measuring accurately, that is another problem. How you will measure a 2 mm thickness if 2 mm, because it has to be uniformly coated and that measuring the 2 mm. Actually, when the thickness is increasing, adhesive failure is increasing.
But any relationship is there? Some equation based or something? It is or depends upon the material it will change, right?
I think so. I couldn't find any
Yeah.
mathematical expression or relation between them.
Thank you.
What explanation it is given is that the stress distribution, it will be difficult if thickness is higher. Whether you can,
Depending on the substrate, because what she said like 2 to 4 mm is very often at least one kind of substrate, right? Completely thin materials.
yeah.
Coating with an adhesive, then 2 mm may be still lower than this. That's it. If you say an example like if you put a plywood sheet, a two plywood is a bigger, thicker sheet. If you want to join, there could be like a higher amount of adhesive. But like ma'am said, higher the adhesive more than required always give a catastrophic failure. It
That is
doesn't
right.
give the improved strength. It is other way. Always give the
Thank you, ma'am, for this wonderful session.
Thank you, thank you. Yes, sir.
One more question.
Ma'am, I may be wrong. In the mechanism of adhesions, you told in that mechanical adhesion, surfaceness, roughness is mandatory for mechanical adhesion. What I got is surface. First, we need to go for a surface treatment, which makes the cracks or openings in it. Then we smear some fibers or fillers in it, and we can get the composites. So, why the need for surface roughness?
No, then we
Mandatory
are
for
applying not fibers. We are applying the adhesive. So adhesive will penetrate into that pores. And once that is joining two adhesive surface together, we are applying this surface roughening, and we are applying this adhesive on that, and join this. So this adhesive on curing, it will harden, it will go and lock itself inside that pores or cavities.
So surface treatment makes
Surface
the
roughening,
substrate
surface roughening.
makes the substrate rough.
Ah,
First it roughens and then only we go for smearing the fillers adhesives.
yeah. So that surface area also increases. Peaks and these valleys will come.
Thank you, ma'am.
Thank you.
Now I request Dr. Habit to give a token of appreciation for Professor Litty Allen.
for me, it is a privilege because I am the mom's student. She's a mentor and guide for me. So thank you so much, ma'am, for all those things. I'm taking this as an opportunity. Okay. So anyway, thank you so much, ma'am, for the presentation. No, no. Thank you. Yeah.